The title of my presentation is Low Cycle Fatigue Damage Accumulation Near Cold Expanded Hole by Secondary Hole Drilling Data. This presentation was prepared together with my colleagues Dr. Vladimir Pisarev and Dr. Svyatoslav Eleonsky. Outline of my presentation. First of all, I'll give brief motivation of present research. After that, we will consider background of damage accumulation approach based on experimental measurement on deformation parameters. Of course, we will consider experimental procedure and fatigue damage accumulation analysis, and finally, conclusion. So, I would like to start from motivation of present research. Widespread situation in aircraft structures when a fast crack initiation process is attributed to high-level elastic plastic strains near stress concentrators, for example, a hole, needs special attention. Stress concentration in some elements of pin or rivet joints, random overload, might additionally contribute in the acceleration of damage accumulation process. That's why damage accumulation eventually leads to substantial reduction of residual life and strength due to low cycle fatigue. The cold expansion process reliably leads to increase of fatigue life of aircraft structures with fastener holes. Optimal design of side joints must take into account local deformation and damage caused by low cycle fatigue. So, quantitative description of damage accumulation is the essential step in this way. Cold expansion of plane hole induces a zone of residual compressive stress around and through a hole, typically extending radially at least one radius around hole. Typical applied expansion levels are ranging from 3 to 5% for aluminum alloys. Damage accumulation quantifying near cold expanding holes due to low cycle fatigue is of importance from viewpoint on scientific as well as applied interest. We suppose to use experimental deformation parameters relevant to the secondary hole drilling as a measure of fatigue damage accumulation process. Theoretical background of the damage accumulation approach based on experimental measurement on deformation parameters. We have introduced into consideration damage accumulation function, which describe a degree of fatigue damage proceeding from evolution of some deformation parameter P. In this equation, this parameter is damage accumulation rate, and M is number of loading cycles. Damage accumulation function can be derived by integration of previous equation 1. Boundary condition in the damage accumulation function D must obey the following equation, and limiting case in this equation is defined as Nm equals to Nf, that corresponds to full failure of specimen under fatigue loading. Damage accumulation function can be given in the following simple equation number 5, where Sd is normalizing coefficient that must be derived from the experimental data for each specific deformation parameter. P as function and M represent a set of experimental deformation p-values after reaching nm cycles of loading. P at nm equal to 0 is p-values obtained in the specimen without preliminary low cycle fatigue loading, and nf means number of cycles before fracture for different loading programs. It should be specially mentioned that employing a normalized value of p as function nm, which are experimentally obtained in different stages of low cycle fatigue, represents the key point that is essential for deriving the damage accumulation function. Conventional normalized parameter p as function nm values can be given in function of lifetime by equation 6. Experimental procedure. We have employed plates with central cold expanding hole for experimental investigation. Initial diameter of plane holes equals to 4 mm. All specimens are manufactured from single material, aluminum alloy 2024 by same manufacturing process. Electronic specular pattern interferometry was employed to get initial experimental information, including two in-plane displacement components, U and V. Also, we employed the secondary hole drilling together with subsequent measurement of increments of principal residual strain by means of ESPI to quantitatively describe damage accumulation in the vicinity of cold expanding holes. This procedure is carried out for different stages of low cycle fatigue. This interferogram demonstrates very high quality of technology that is used for cold expanded process. It should be also noted that deformation response revealed on sign B, its outlet mandrel surface, exceed similar parameter on sign A, corresponding inlet mandrel surface. Two low cycle fatigue problem has been investigated. Strain range is a constant value and equals to 320 megapascal. Stress ratio was minus 0.4 and minus 0.6. Deformation response to secondary hole drilling expressed in terms of interference Fringle number, evidence that residual strain relaxation in longitudinal direction coinciding with applied force line exceed relaxation in transverse direction U. Fatigue damage accumulation analysis. The plots of this slide demonstrates how stress ratio has influence on evolution of residual strain in the vicinity of cold expanding hole in the case of outlet mandrel surface for stress ratio minus 0.4 and minus 0.6. values of increments of secondary hole diameter in principal stress directions were obtained at different stages of low cycle fatigue. These data assure construction of normalized dependencies of impaired parameter against of lifetime, which provide explicit form of the damage accumulation function. So, the effect of stress ratio on damage accumulation rate is quantitatively described in the case of stress ratio minus 0.4 and minus 0.6 under constant strength range 320 megapascal. It can be seen that a more intensive fatigue damage accumulation in the vicinity of cold expanding holes is observed at stress ratio minus 0.4. The following conclusions can be drawn. Secondary hole drilling method is developed to quantitative assessment of fatigue damage accumulation in residual stress field near cold expanding holes. Values of increments of secondary hole diameters in principal stress directions are obtained for different stages of low cycle fatigue. Normalized values of this residual strain obtained at different stages of low cycle fatigue are involved as a current damage parameter. The effect of stress ratio on damage accumulation rate is quantitatively described in the case of stress ratio minus 0.4 and minus 0.6 under constant strength range 320 megapascal. There is a more intensive fatigue damage accumulation in the vicinity of cold expanding holes at stress ratio minus 0.4. Thank you very much for your attention.